You still see my screen, right?
Yes.
Okay, good. So this time I'll start myself, so I'll know what's going on. Okay, so I'll continue here, and I wish this were the first talk. So here I'll talk about the single molecule magnet, the dimers. This is without the substrate. And again, this is our collaboration here with the colleagues at UF from Hyping's group. And my outline is that I'll tell you a little bit, which I've already mentioned and was mentioned also in the earlier talk. I'll mention some of the properties now of these two dimers. Basically, look at the spin analysis, the HOMO-LUMO gap, and show that the magnetic easy axis is very much along the directions that they see experimentally, give you some of our results for calculations of the magnetic anisotropy and exchange couplings. And this was done by Rainier. So basically, I think I'm going to skip this talk because you all are very familiar with why we are talking about single molecule magnets. And the main thing here is again, these are the dimers that that I mentioned. 3 manganese atoms coupled ferromagnetically in this case, and coupled antiferromagnetically in the other case. Of course, that coupling depends on the ligand that you use, and these are 2 different ligands. The fact that one is ferromagnetic and the other one is antiferromagnetic, it basically is shown from these measurements that were taken by Hill and Christou, and this is the sign of this is based of the exchange bias is telling you that this is antiferromagnetic, and the lack of it here is for the ferromagnetic case. And again, the molecules are very weakly interacting. So essentially, let me skip this. We use density functional theory based methods and do apply DFT plus U, and then you make the usual follow the usual procedures for calculations of J. I'll show you that in a second. So calculations of J, for example, is used by either the Noodleman's method or the Ruiz's method, and I will show you a comparison of that. And so basically what we calculate in this case, the spin, the J12, which is basically this interaction over here, and then we calculate J's, which are the interaction between these spins, and the J primes, which are the interactions between these spins, because again, this is not, it is more of an isosceles triangle rather than an equilateral triangle. So these J and J primes are different. Okay, so one of the things that I mentioned in my last talk was that there was an issue in terms of getting the spin to come out right. So spin for the sorry, this should be 0, and for the ferromagnet it is 6, and we get 5.5, regardless of what we use for the van der Waals functional. And so then the question was, well, why is that? How can that be removed? And we were very relieved to find that in experiments, these molecules actually are charged. They have a charge of +2, and so when we did put +2 in our system, we got the results that we expected, which is that we got a total spin of 12 for the ferromagnet, and that of 0 for the anti-ferromagnet. So that was nice. This is where I show you the molecular orbitals that we have calculated. So this is the HOMO-LUMO gap. And again, I won't have time, but when we do charge transfer analysis, this is really a good way to go about for that. So what you're seeing over here, this is the molecular orbital for the ferromagnet. And this is the one that we find for the neutral, and this is the one that we find when you have the charged dimer, okay? And bear in mind that the charged dimer is really the one that we think they see in experiments. And so the same thing here, then when you do this analysis, what you find is for the ferromagnet, if you had the uncharged system, again, the minority spins are the ones that are very close to the Fermi level. And then for the charged one, it's, of course, you know, the system is charged, and here what you have is a rather different situation over here. Okay, so we can go into details if you're interested, but these actually allow us to then look at how charge transfer can take place in the presence of the different substrates. Here what we did is we wanted to find out the easy axis for this, and the easy axis turns out to be this direction, in this direction, and that is, say, we are calling that the Z direction. That's the one that's perpendicular to the plane of the molecules. And what you find is that this is the magnetization in the plane, and so that is the easy axis, and is then along the Z direction. This the same thing happens for the ferromagnetic and then for the antiferromagnetic dimer. The next calculation that Renier did was to look at the magnetic anisotropy, and I should have given you these numbers in degrees in Kelvin, but I don't. I have it in millivolt, and we still have to check on these to make sure that the calculated quantity is exactly what could be measured. So it is of the order. It's a very small in these cases. The second thing that we have here are the calculated values of J, and this is something where we were wondering whether DFT works well or not. And so what you have here is this is the experimental value of the various J's that we have over here, and these are the calculated. You can ignore the ones below. Let's look at just the Noodleman's method of doing it. And this one is calculated in the experimental. We think that looks quite promising. A good agreement here. We don't have as good an agreement over here, but these are really very small numbers. Okay, so this is actually this coupling here, J12, between the molecules, and that experimentally has a positive sign. We have a negative sign. And so that was something that we were concerned about. And so what we did here is we looked at essentially the effect of U in this case. So this is where we're applying the Hubbard U parameter. And as you realize that, when you put U in your calculations, you are bringing in, it is no longer ab initio, right? I mean, we have a parameter now to work with. And what we find is that you can switch the sign of of J. So this is J12 that we've looked at. You can switch the sign of it for both the ferromagnet and the antiferromagnet by applying a very small amount of U. So this is something that we think that it is so small that it is probably not worth worrying about. And for all practical purposes, this J12 is essentially really zero. It's very, very small. So I guess I spoke very fast over here. So what we have done is we have carried out these calculations based on DFT and a little bit of DFT plus U. What we have shown is that the spin values that you get for both the ferromagnet and the antiferromagnet gives good agreement with experiments when we assume that the molecules carry a charge of +2, that is 2 electrons have been removed from the molecule. And we confirm that the easy axis is in this direction, that is in the direction perpendicular to the plane of the Mn3 of the 3 manganese in the 2 molecules. And we find that the J values are actually very small, and we could get excellent agreement, but we don't know if that would really make any sense. So that will leave me with a little bit of time for questions. So thank you very much for your attention.
Thank you, Talat. Thank you for a couple of very nice talks. I don't see any questions coming in yet, but oh, here's one. Oh, it says Zara is here to answer questions if Talat would like. That's from Mark. Okay, so I have a question that sort of interleaves both talks. You very nicely were able to calculate anisotropy for these dimers, and so I'm wondering if putting the dimer onto a surface like graphene or boron nitride, if that has any any substantial effect on the anisotropy.
Yes, so we, in fact, great that you asked that, because that was what when I had asked you that I would change it. So essentially, I have the results for that. So Renee did do those calculations. And the quick answer is, and let me see, maybe if okay, let me see if I have it here. If there is a place where I have it, I'll, okay, just a sec. Oh yeah, here it is. Okay, no. Okay, so the answer is there is some effect, and the effect is more when it is on yeah, here it is. Okay,
Ask him to clarify what he means.
Those are J values. Yeah, okay, so there is some effect on the dimers. It is, I can give you the numbers. Maybe I should just send those to you. It is, our conclusion is that the effects are small enough that if we were going to be doing these measurements that Art is setting out to, that the properties of the dimers will be protected. So for example, the one value that I showed you that was 26 in those units, that has changed to 18. And but the J12, which was the important one, that did not change significantly.
Okay, thank you.
Okay, I got it. I got that. Do you see this one?
Okay.
I will
So,
just put it there. Yeah.
So here's a question from Jürgen Schnack. Do you also evaluate the anisotropies D and J? Or yeah, is there an anisotropic J?
That is that is something we haven't done, but yes, that is exactly the idea. We do need to do that. And so we actually will be calculating the uniaxial magnetic anisotropy, and we'll have numbers for that very soon.
Okay, great. All right, well, thank you. I don't see any other questions, and we're out of time.